All right. So I'm just going to start today. Today we're going to see an example of column generation. Who knows column generation here? Raise your hand, somebody. Somebody ever heard of column generation? Huh? Yeah? All right, so you know, like, sometimes you have this huge problem, that it's basically impossible to enumerate all the variables. So since you can't even enumerate all the variables, just imagine try to do the CPLEX method or try to apply branch and bound to a problem that you can't even put all the variables in. I mean, that the motivation for column generation is that you know how you in CPLEX method, whenever you wanna iterate, on each iteration you calculate the reduced cost and choose a variable which has a negative reduced cost, and you choose that one to go into the base, and then keep on doing that until all the reduced costs are 0 or positive, right? Okay, so basically, if you have a lot of variables, just computing the reduced cost for one iteration is too expensive to do on time, on computational time. And especially if you're going to be doing branch and bound and solving a relaxed version of the mixed integer program on each node that you're branching. So just imagine trying a big enough problem. It's going to be really expensive to calculate. So what column generation does is that it starts with a problem which we're going to be calling master problem. A master problem which has only a subset of your variables. Only a subset of the variables. And so when you solve the linear relaxation, okay, how to explain this? Since you have only a subset of the variables in your problem, you want to add variables which are going to be candidate to enter the bases. You don't want to just put all of the variables because, I mean, you know that when you calculate reduced cost, some of them are negative, some of them are 0, some of them are positive. So you just want those variables which are going to have negative reduced cost, right? So in the master problem, we're going to start with only a subset of variables, and then we're going to use another problem that we're going to call a sub-problem, which objective is going to be finding those variables which are going to enter the basis of my master problem. So the interesting part here is that you only put into the master problem, the problem that you're interested on, you put in your master problem only variables that are they're going to be entering the basis. So we're going to solve a master problem that we're gonna solve the linear relaxation. We're gonna use the dual variables from that problem. We're gonna update the sub-problem, and the sub-problem is gonna give me a new variable which I'm gonna be adding to the master problem. And since that variable, I'm gonna be choosing it such that the reduced cost is as minimum as possible, so that it's negative. And then I'm gonna put the variable in the master problem, and I'm gonna again solve the linear relaxation, transfer the dual variables to the sub-problem, and then again try to find a variable in the sub-problem which has negative reduced cost, and keep on going like that. To the point at which, when I'm solving the sub-problem, try to find a variable which is gonna have the smallest reduced cost. There's going to be a point at which the subproblem is not going to find any variable with negative reduced cost. It's going to find variables only with reduced cost equal to 0. And then we're going to know that there aren't any more variables that I can put on the basis on the master problem. All right? So then I'm going to be finishing, and I'm just going to solve then the problem with those variables that I already generated. So what I'm doing here is I'm only adding variables that are going to be interesting for me. All right, not all the variables. Okay, and to do this, we're gonna do an example. I'm gonna and it's so long. It took yesterday. I was coding this, and it took me like 5 or 6 hours. So what I'm gonna do, I'm just gonna ask you to pay attention, and instead of writing the code, I'm just gonna debug what I did yesterday. Okay. So I'm gonna go through all of my code line by line, explaining what I did, okay? And I put all the code already is up on internet, so then you can try it and try to do the same as me. All right. So first, I said that column generation is useful for big problems. So this is a big problem. This is a vehicle routing problem with time windows, which means that you have a depot. Maybe you have a depot and a destination, doesn't matter. And you have a set of customers. The set of customers is going to be represented here by C. So each customer has a demand. Each customer has a time window. Say you're calling from your house, and you have 5 friends over, and you want to go to the airport. So you call a taxi, and then you have a demand, and also you have a time window because you want the taxi to be there between, say, 10 and 10:20. All right. So here every customer has a demand and has a time window. So the demand is going to be represented in the problem by D for each customer, and the time window is in this constraint. So the time window for this customer is between A and B. A and B is the time window for each customer. And we're going to have a capacity on the vehicles. Okay, the capacity of the vehicle is going to be Q, which is here. All right, so that's all you need to know. So what we want to do is minimize the total cost. Being here the total cost, we're just gonna take the time. All right, so we're gonna be minimizing the total time, which is here at the top, and Cij is gonna be the time from going from the node I to the node J, and that time is gonna be also including service time or the waiting time at the node. I mean, if you go and pick up something to some customer, and then it's going to take you maybe 10 or 15 minutes to stay there. So you have to take into account that time as well. All right? Okay. This problem, as stated here, this is just one problem, and this problem is too big to try to solve, as it is here. Okay? I mean, you have a binary variable with 3 indexes. I mean, if you're facing a binary variable with 3 indexes, you're in trouble. I mean, if you're gonna be doing research or something, and you come across something like this, and then you know that you're gonna have at least 100 nodes, 100 customers, and you're really expected to try to solve this to an exact solution. Okay, I don't know. I don't want to ruin the dreams, but you won't be able to solve it. Okay. So we're gonna try to get to a close to optimal solution rather than getting the optimal solution, which it could take you maybe a month, a year. I mean, if you make it big enough, it literally can take you like the whole life of the universe, and still you would run out of time. Seriously, I'm not I'm not exaggerating. All right, so we're gonna decompose this problem. We're gonna decompose it into a master problem and a subproblem. Master problem has dun, dun, dun. All right. So this is going to be the master problem. So you see that it is much smaller. So all I'm doing here in the master problem, say I have a variable which is going to represent a route, one path, okay, for one particular vehicle, any vehicle. And in the constraint here, I have that this A is going to tell me if that path cover or not the customers. So with this constraint, I'm just making sure that the variables, that the path that I'm going to be choosing cover all the customers. All right. So why do I do this? Now, before I had a variable which would say vehicle K goes from I to J. Now I have a variable which just says I'm gonna be doing path P. Okay, and if you imagine this, P would have to consider all possible paths, all combinations. And okay, so that part is the part that you can't even try to put in here. So what we're gonna do is that use a smaller problem, the subproblem, which is gonna be this one. This one, if you see this one, is basically the same problem, the original one that included all of the vehicle, but this one doesn't have the index K, if you see there. I, J, K, the K is not there. So this problem is a fraction of the of the main one we had at the beginning. And what this one does is just generate path for one vehicle, and once you generate a path here, you put it in the master problem, the small problem that we saw before, and you iterate, okay? And the interesting part is that this problem, the subproblem, has a modified cost, all right? So it's the regular cost that we had in the original problem minus the value of the dual variable, okay? And that dual variable comes from this constraint. Now, I'm not going to go into details on how to show that this is true, what I'm saying. I just need you to understand this, because this is what I coded, all right? So what I coded is I have a master problem, a subproblem, I solve a linear relaxation of the master problem, take the dual variables, update the cost of the subproblem, solve the subproblem as a mixed integer program, use the result to generate a new path, include that path into the master problem, solve the linear relaxation of the master problem, get the dual variables, and so on. Okay, so I'm going to be jumping from the master problem to the subproblem until the result of the subproblem, the objective value of the subproblem, is 0 or positive. Okay, then I'm gonna know that it's not possible to generate new variables that are gonna be entering the basis of the master problem, right? All right. So I have customers. I have two depots: the starting depot and the finishing depot. What else? I have I have the path. So I have a master problem, I have a subproblem. Okay, so you have all of those things. You have, since we're going to be coding in Java, you have to think of those things. You have to think as objects, right? You have to think that you're gonna be using those objects. You're gonna be using customers, depots. You're gonna be using path, a master problem, a subproblem. So you probably need to create classes of all of those objects. So I want you to look what I created here. Okay, so I created a whole class, which is in the website of the community, so you can download it from there, which is called column generation. Okay, and I also built in there 6 subclasses. Okay, 6 subclasses that I'm gonna be using there, and all right. So I have a node, and I have depot and customer, which depot and customer are nodes. So nodes is like a node can be a customer, it can be a depot. So I have the path, master problem, and the subproblem. All right. Okay, so I don't have time, so I'm just gonna start debugging and explaining line by line. Okay, so try to follow me, and please stop me if you don't understand. So far, are we clear? So we have a master problem and a subproblem that generates path, and we're gonna be jumping from one to another. Okay. All right. Okay, so I'm gonna be using the data R101 that if you go to internet and just Google Solomon, which is the author of the article that I have there, this dude is really famous for vehicle routing problems. And there is a set of benchmark problem that people uses to measure the efficiency of the algorithms. The optimal solution for these problems are known. Some of them are not known yet, so you might be willing to do some research on that to find the optimal solution. But these problems, they have people use them to compare algorithms from each other. Okay, so if you want to compare your algorithm, if it's more efficient or less efficient than another, you use benchmark instances. So there are a lot of here, and I'm using this one. And I have a list of customers, their coordinates, demand, and the time window, and the service time. The first node always represents the depot, okay? The first node represents the depot. So I have this, I put it on a, I put it on an SQL server, which is running a computer in Bellhop. And I'm using this database seminar, which you will all have access temporarily, like, I don't know, for a month or so, until I cut you off. You can just go in here and you can read and write data, but can't modify anything else. So I have here, where is it? Here. I have that instance. I'm gonna put more instances so you guys can play with it if you want. All right, so that is so I have that data there, and I'm gonna be running it. Okay, so okay, so in this case would be stepping into. Okay. So I create an instance of the column generation class. Okay, I need to read the data. So the data, just bear with me here. What I'm doing here, I'm connecting to the database, okay? This is standard code. The computer that I'm using is this one, okay? All the computers that are plugged into with the wire, the network wire, this computer that are all across the university, they all have a domain, so you use that. And the database that I have there is called Seminar, and this is the username, the password. And I'm calling only the data from the instance which has the name that I'm interested in, okay? And then I'm recovering what this does is that pulls out the database and goes row by row, asking for all the data until it goes until the end of the query. Okay, so that's what I'm doing here. And every time I do that, okay, so I'm collecting all the data row by row. And when I have all the data on one customer, I create that object. All right, so I create a new customer every time until it finishes. Then I create the depots, reading the same way from the table depots this time. Okay. All right, so let's just move on. All right, so now after reading the data, I create the master problem. I'm gonna kill this. All right. So the master problem. In the master problem, this is a master problem. So I have only one constraint for each customer, and one variable for each path. And I have and I have, since I have for each customer, I need a dual variable. I'm gonna be storing the dual variable here, the dual values. Okay. Oh man. All right. So create the model. The CPLEX engine Oh my God. All right. Okay, so the CPLEX engine, then oh my God. All right. Okay, so I have an expression which is going to be the total cost. I make it that it's going to be the objective value and to be minimized. And for each customer, I have an array, which is actually a map. So for each customer, and all of those customers are in this variable, I create a new constraint, which I'm going to be storing in this variable. This is an array of constraints. And here I'm creating the constraint. So, okay, so the difference here from what we learned last week is that what I'm creating here, I'm creating the limit, like a range rather than a constraint, because I don't have the variables yet here. So I'm just saying, okay, I'm going to have a constraint which is going to go from, in this case, from 1 to 1. So I'm creating an equality. But at this time, at this moment, between 1 and 1, there's nothing. Okay? So I'm just creating there. Because I'm going to be adding the variables as I go, I just need the constraint to be there, and then I'm going to be putting the variables. Okay? So that's why I create a range rather than a constraint. If you create a constraint, you need to have all of the variables already there. All right. So that's all the model for the master problem. All right. So and since the master problem to this point doesn't have any variable yet, so I need to create variables. So one criteria that the default criteria is just to create a path for one vehicle to go only to one customer and do that all across the customers. So my starting variable are only going to be like, since in this problem I have 100 customers, so I'm going to start with 100 variables, and each variable is going to go only to one client. Of course, that is completely expensive, but that's a starting point. For a massive problem, you need variables to start with. Otherwise, you can't solve the problem to update the subproblem and generate new and better routes. So you need to start with a set of problems. So that's why I create here the default path. So the default one are going to be, so here I'm doing one for each customer. So one for each customer, and the path goes first to the depot, then to the client, and then to the depot again. And with that information, I create a new column. So this is how I create variables. A variable is a column, so that's why it's column generation. So now I have the models, all right? So I have an objective which doesn't have anything yet, and I have constraint that they don't have any variable yet. So here I'm creating a new column, and here I'm adding that column into the objective value of the master problem, okay, with this coefficient. So it's right here is making whatever it has on the objective plus this new variable multiplied by the cost. So since it's going to be now the first one, it's just going to have that at the beginning, all right? So, and now for each customer, and okay, so this is interesting. So you have this new column, and you need to aggregate it with all of the things that with all of the constraints in which you want it to be. So, and you have to use this and there to, it's like saying, okay, so whatever I had before and this as well, and you go through all of the customers. So, all right, so, and here you are creating a column into this particular constraint. Remember that I store the constraints. I put them in an array, okay? So now I'm calling that array. You can't just create the constraints and not assign it to any variable, because then you won't be able to make a reference. I mean, to call them. So here I'm calling each constraint, and I'm saying that it's going to be this value here multiplied by the variable. So what I'm doing here is doing this part. For each one of the customers, I'm making the multiplication A and the variable. Okay? Now, I'm creating one path for one customer. So even though here I'm going through all of the customers, this A is going to be one for only one customer. And I'm going to do that for all the customers. So I'm going to start with 100 variables. Each one is going to go only to one customer. And so here I officially create the variable and put it into CPLEX, okay? At this, the last step. Okay, so, and this method here is general. So always that I'm going to be making a new variable, I'm going to be using this procedure. All right. All right. So in the master, I'm creating the master problem. I create the model, I create the default path, and okay, so this is another interesting part, and I'm making the configuration. So I need this to be solved in a certain way. So for the master problem, I'm gonna be making, all right, so here I'm saying that node selection is gonna be 1. 1 in this case mean best bound. You can find out all of the node selection strategies just by typing in Google. All right, so you have best bound, best estimate, best alternative estimate, something, depth first. And you have, yeah, those are. So number 1 represent best node. And branching direction. So when you branch in a variable, you need, if you want to branch up or branch down, right? So in this case, I'm branching up. It's better to branch up because you're going to make the variable be 1. So that's going to make all of the other values be 0. So it's easy to solve. If you branch up first, then all of the rest are 0. So you fight on that node faster. All right. If you make it branch it down, then you're going to be branching down all the time. You're going to be generating a huge tree before starting fight on the nodes. All right. So that's why I do that. All right, and this is only to display. It's going to be displaying for the when it's solving the MIP, but not when it's solving the simplex. All right, so that's the master problem. Okay, so I'm here. I haven't started anything yet. All right, so now I'm going to be doing the sub problem. The sub problems. What is this? Okay, so I'm creating a new set of constraints. I'm going to create the model. And this model is bigger. This one here is represented. Okay, so I'm going to be trying to write this. All right, let's go. Okay, the engine, the variable x is only ij, so here's the I, and then the j is, and I name it. All right, for all nodes. This is for all nodes. Then the s, this s that is here is also a variable. This one is continuous. So it goes from 0 to infinity. Some parameters, the m, and the paper. And the paper, there's an expression for the m. For the m, it's just you calculate it. That's one thing. If you have a problem and you're gonna be using a big m, you gotta make that m as small as possible. Otherwise you're gonna be having numerical complication. So you don't want that. If you have an m, just make it as small as possible, right? So this is what I'm doing here. I'm choosing the smallest m there can be for that constraint. The capacity, the objective. Okay, so here again, I'm defining the objective, but I'm not writing what it is because the objective changes on every iteration. So I need to put it in somewhere else. Okay, so later on I'm gonna be showing that. So the capacity is only one constraint, and I make the summation for all I in customers and j and all the nodes. I added, each one has a d and a multiply, right? First constraint. Then the constraint to start from depot, the same way. Remember that I need to construct the for loop. I construct the for loop, and every time I add term, I'm making the summation, right? The flow conservation, this constraint here, that one is for each customer. So the constraint is inside the loop. This is okay. You gotta be careful with this. Whether you gotta know where to put the constraint and where to reset the numerical expression. So since this constraint is for each customer, you need to reset the numerical expression and the creation of the constraint inside the loop. Not like the previous one, which you reset the numerical expression and put the constraint outside the loop. This is, you only use the loop to make the summation. But in this one, you put it inside. And this one is actually mixed because you use the second level loop to make summations. All right. The other constraint, and at the depot, the subtour elimination. The subtour elimination is for I and j's. So the reset of the numerical expression and the creation of the constraint is inside the second loop. All right. The last one, the time windows. And I had to add this constraint because this problem is set for x that are, they don't have the same I and they don't have the same j. And so basically here, I'm making sure that the variables that are supposed to be 0 are 0. So for example, here I'm saying that you can't go from the end depot to any node. I mean, you would be going backwards. You can't go from any node to the starting depot, of course, and you can't go from one node to the same node. That, okay? Just making sure of that. All of that has to be 0. That's why that constraint there. So this is the easy part. Actually, writing the constraint, writing the model is the easy part. I mean, writing all of the rest, making sure that the data is well loaded and how to process and post-process the data, that's more complicated. All right. So that's the creation of the model. Okay, so priorities. You can set priorities. You can tell CPLEX which variable to branch in first. So this is easily done. So basically what I did here is, okay, I'm gonna be branching first on variables, on the variables that decide where to start the path. So I'll be choosing first the X that goes from the depot to some customer. I'm gonna be putting all of those variables with the same priority. So this is what this is it. So for all J's and the customers, I'm gonna be setting a priority to this variable. So for all the X that go from the depot to any customer, I'm setting the same priority. You set the priorities here. I put 1. This is my only priority that I'm putting all the same. You can put any number there. The bigger the priority, CPLEX is gonna go there first and then go to the next. If that variable happens to be 0 or happens to be an integer value, then CPLEX is just gonna go to the next one. All right. So because it's only priorities make sense only for fractional variables because you want to branch on those. All right. So that's for the priorities. The configuration for this one. I use the same reasoning. I choose the best bound as the node selection strategy. I'm gonna branch upward, and I'm gonna have a gap. I'm gonna accept a 10% gap from the optimal. All right. So I'm not gonna be waiting until I get the optimal solution. I'm just gonna stop whenever I'm within 10% of the optimal solution. All right. And okay, so callbacks. Callbacks. So I created here also callbacks. You use callbacks whenever you can use it at different levels. I use it here so I can introduce a piece of code made by me into the branching bound process that CPLEX does. So every time CPLEX solves one node before doing something else, it's gonna do what I tell it to do and then continue. So that's what callback do. Okay, so in this case, I'm using callback only to read information. You can use it for a million things, but right here, I'm just gonna be using it for stopping the branching bound process at each node. So so how this works? I have inside the subproblem. This is for the subproblem only. Inside the subproblem, I create this class. I mean, I create the class, I define it, but I use a class that is already in CPLEX. So I use a class that is already in CPLEX. I take all of these properties and I add some more properties that I wanted to have. Okay, because why would you want that? I came across because I needed to add this because you have a 10% gap, and you can set up a relative gap and you can set up an absolute gap, right? But what I needed is that if it reaches a certain value, the objective value, then I wanted to quit. And that you can't have with either of the gap, okay? And also, I didn't just wanted to have one criteria to stop it. So I wanted to, like, if this happened and this also, then finish. Otherwise, if this other thing happens, then finish as well. And if none of those things happen, then go away. So I mean, CPLEX has only so many things by default, but you can use this to make it do whatever you want. So, for example, this piece of code here, this piece of code is being called every time the branch and bound finish one node. Before branching in any other variable, it's going to call this, it's going to execute this piece of code. So it's going to be doing, so all it does here is that if it hasn't been aborted and there is an incumbent, then I measure the time and I wonder if that incumbent value is good enough, or if the time is bigger than the one that I needed, or if the best value, the lower bound, is bigger than 0. I mean, if the lower bound is bigger than 0, then I know already that the whole problem is, I have to get out of there. I mean, I'm not going to get out of this code that is going to be negative. So if any of those conditions goes, I abort the branch and bound, and then branch and bound finish it and saves whatever solution it has to that point. And all right, so my God, can't believe I've run out of time. Okay, even if I wanted to, I can't explain everything. All right, what do we do? Okay, who's interested in column generation here? There is some people. I can work with 5, so I'm fine with that. All right, this code is going to be posted. Yeah, there's access to the there's access to the database on that computer on Bell. In order to run it, in order to try to run it, you need to have installed. No, you just need to put this one here. You need this driver to put to be there. You don't need to have this one, okay? You don't need to have that one. But if you want to make your own database, you do need to install that, and you make it in your computer, and you can just use your computer as the as a database. Yeah, that's it. I wish I could have more time. Thank you.
I need to find something for your attendance. If you're interested in more content, come on down. I'll take your email address.